Greetings and welcome to our Coastal Morphometric Smart Data video prepared for the 2021 Coastal Dunes for Resilience workshop. My name is James Jackson. I'm a civil coastal engineer with Environmental Science Associates, and I'm here to talk about how we can monitor dune systems in the state and beyond to better understand site-specific dune morphometrics for the purpose of utilizing dunes as natural infrastructure. In this short video, we will discuss a conceptual model for natural dunes, proposed smart data collection, and connections to natural infrastructure design guidelines. Let's first start by reviewing coastal water level definitions. The total water level, or total wave run-up, on a coastal shoreline is the sum of multiple components: the still water level, including astronomic tides, the static setup caused by storm surge, including atmospheric pressure, wind setup, the dynamic setup from wave groups that meet the shore, and finally, run up from individual waves. Total water levels govern the morphology of coastal dunes. During the winter, stormier ocean conditions will erode beaches and impact the dunes behind them. Over summer, long-period waves build the beach width back, which allows dunes to recover depending on local wind climate and/or management actions. Let's take a closer look at how water levels affect dune morphology. The graph here shows the probability of still water levels at different elevations. The dashed line depicts still water level probability of occurrence within the normal tide range, including storm surge known as non-tidal residuals. The solid line shows the probability that the still water level is exceeded across that same tide range. Let's now consider the addition of waves. Wave setup and run-up raise the distribution of water levels, the amount of which depends on the local wave climate and shore geometry. Key features on a coastal profile can be related to water level exceedance. A summer dune toe that is relatively higher in elevation may be exceeded part of the time, whereas during the winter, the dune toe elevation will drop as storms erode the beach and impacts the dunes more frequently. The beach width varies throughout the year, affecting wave run-up and thus the total water levels that may reach the dunes. For example, let's take a look at coastal morphometrics in real life at Lindemar Beach in Pacifica, California. Restored in the 2000s, you can see the dune toe, which is met by total water levels at varying frequency throughout the year. Recent high tide line can be seen in the damp sand and the beach width that's fronting these resilient dunes. By monitoring dune morphometrics throughout the year at natural and restored sites, we can better understand the natural locations and elevations that dunes could persist on the profile, given local total water levels. This enables practitioners to evaluate the feasibility of dunes as natural infrastructure adaptation in coastal communities. For example, consider the offset shown from the dune toe to the shoreline. This minimum beach width in front of a resilient coastal dune is around 100 feet in the summer, per recent guidelines that ESA developed with the Nature Conservancy and others. Tiffany Chang, my colleague, coastal engineer at ESA, will now explain the study and design criteria developed for dunes.
As part of the California Fourth Climate Assessment, ESA, with the Nature Conservancy, Point Blue Conservation Science, and NOAA's Site Sentinel Cooperative, developed the Natural Shoreline Infrastructure Technical Guidance for the California coast, which helps users evaluate the potential for implementing natural infrastructure, such as dunes, at their site, based on physical parameters like tide range, wave exposure, total water levels, beach width, and foreshore, backshore, and other planform geometry. This graphic shows ballpark estimates of minimum dimensions required for dunes implemented as natural infrastructure to protect backshore assets and/or enhance beach recreation and ecology in California. The available space should exceed the sum of the total constructed dune footprint and the dry beach width. Smart data collection can inform the seaward edge of the dune, which is defined by the location where total water level reaches infrequently, like 10 days per year or less, and where dry sand area during the summer provides a sufficient supply of wind-blown sand to rebuild dunes. The minimum cross-shore extent of the dune system is approximately 50 feet, which encapsulates the footprint of the dune geometry, including the crest width and side slopes. The recommended cross-shore extent of dry beach ranges between 100 to 200 feet. Higher widths will limit wave attack and provide a source of wind-blown sand onto the dunes from onshore winds. The minimum alongshore length of a dune system is on the order of 100 feet, while the maximum is set by the length of shore that satisfies the two conditions set forth for total water level and dry sand area.
Thanks for watching. Now go enjoy the beach.